Good afternoon. Welcome to our first session of the afternoon. We had two wonderful keynotes, and I'm delighted for the next session on addressing our wildland fire weather needs. And without further ado, I am kicking it over to you, Bill Mahoney.
All right, thanks, Jen. Good day, everyone, and welcome to session one of the Washington Forum. I'm Bill Mahoney, the director of the Research Applications Laboratory at NCAR, and the previous commissioner of the AMS Weather, Water, and Climate Enterprise Commission. And I'm the moderator for this session, which is titled Addressing Our Wildland Fire Weather Needs. We really have a fantastic expert panel lined up, and the speakers are each going to share their thoughts on a variety of wildfire topics, and then they're going to lay the groundwork for what I hope is going to be a robust community discussion. As an introduction, let me just say a few words about wildfires. Wildfires continue to dominate our landscape and the news cycle, as you're probably well aware, as our forests become older, denser, drier, and damaged by insects and disease. Human ignitions continue to be a major factor in fire starts. Humans cause about 60,000 fires a year. But once wildfires get ignited, they tend to be larger and burn hotter than in previous decades, and that's the major problem here. As you know, there's a substantial wildland fire science program being discussed by Congress, which is aimed at expanding wildfire knowledge and accelerating technology development so the nation can improve forest management, rangeland management, building standards, urban planning, and the wildland-urban interface, and our response to wildfires. Fire science is also very complicated as it involves multiple disciplines, including forest and rangeland ecology, fire dynamics, atmospheric science, land process physics, combustion physics, observational science, and social science for understanding risk communication and human behavior under stress during disasters. Wildfire science also involves a lot of organizations covering the public, private, and academic sectors, including NOAA, the USGS, NIST, the USDA, Bureau of Land Management, Forest Service, National Park Service, the National Science Foundation, NASA, and the research and operational communities. So there are a lot of players in fire science. We can't cover all the ground today, but I asked the panel to focus on a few topics such as trends in wildland fires due to climate change, human interventions, changes in the fuels and the built environment, especially around the wildland-urban interface, unmet needs for wildland fire weather information and services, urban fire research, mitigation and predictive capabilities, science and technical capabilities required to advance wildland fire behavior prediction, risk management from a utility perspective, the promise of emerging technologies, and barriers to adoption of new capabilities. So without further ado, let me introduce the panelists. Each panelist will make a short presentation, and then we will open up for questions at the end. And questions will be captured using the Zoom chat feature, so please drop your questions there. First up will be Dr. Tim Brown. Tim is the director of the Western Regional Climate Center at the Desert Research Institute, where he established and directs the program for climate, ecosystems, and fire applications. His primary academic interests include wildland fire weather and climate connections, the wildfire environment, applications development for wildland fire management planning, and decision-making and policy. He is graduate faculty in the Atmospheric Sciences program at the University of Nevada, Reno, and was formerly Monash University adjunct in the School of Earth, Atmosphere, and Environment in Clayton, Victoria, Australia. Our second speaker will be Brian D'Agostino. Brian is the Director of Fire Science and Climate Adaptation at the San Diego Gas and Electric Company. As director, Brian is responsible for meteorology, fire science, and climate adaptation initiatives. Brian joined San Diego Gas and Electric in 2009 and oversaw the development of the company's weather network, which is one of the nation's largest and most sophisticated privately owned weather networks. Brian is the former chair of the AMS Energy Committee and is a founding member of the AMS Committee on Wildfire Weather, Technology, and Risk. Brian also sits on several advisory committees specializing in climate adaptation and fire science. Brian's a graduate of Plymouth State University. Next, our third presenter will be Robin Heffernan. Robin is the National Weather Service Fire Weather Science and Dissemination Meteorologist located at the National Interagency Fire Center in Boise, Idaho. Since 2011, Robin's been responsible for leading several technological and science-based efforts for the National Weather Service Fire Weather Program, as well as integrating these efforts into fire weather operations. In addition, she manages the dissemination of fire weather information, as responsible for the training of incident meteorologists, IMETs. Robin also serves on several national committees, subcommittees, and teams, including serving as current chair of the National Wildfire Coordination Group Fire Environment Committee. Our final speaker will be Nelson Breiner, who is a chemical engineer and chief of the Fire Research Division in NIST. The division develops and utilizes measurement science, fire protection technologies to enhance the disaster resilience of buildings and wildland urban interface communities, firefighter safety and effectiveness, and homeland security. Nelson's research interests include studying aerosol particulates from smoke, including smoke from wood, plastics, and crude oil fires. He supervised the large fire research laboratory, facility laboratory, led the firefighting technology group, and participated in the reconstruction of a number of multiple fertility fires that you may have heard of, including the Astoria hardware store fire in New York, Station nightclub in Rhode Island, and the Sofa Superstore fire in South Carolina. He was also the first leader of the Wildland Urban Interface Fire Group, which works to understand the vulnerabilities of residential homes to fire exposure in order to develop designs and materials that would harden communities against WUI fires. So clearly, this is really a fantastic panel, and I'm really looking forward to their presentations. So let's switch gears. First up is Dr. Tim Brown.
Thank you, Bill, for that introduction. And I think you said it quite well, how complex the wildland fire environment is. We could go to the next slide, please. This is a quote from Dr. Stephen Pine, actually from back in the 1980s, and about fire behavior. But I think the key thing here is that wildland fire does not merely resemble a climatic or meteorological phenomena, it results from them. And as a result of that, I think there are really two aspects of wildland fire to think about. So if we could have the next slide. The first, I think of this as climate enables fire. And in that left picture, we can see tall fuels, fine fuels on the left. This is the type of fuel that really carries fire. And on the right is pine beetle kill in forested area. That's a result of warming temperatures, drought conditions, things that stress the forest and allow something like these insects to take over millions of acres. The next slide, weather drives fire. And in some cases, fire drives weather. This is the pyro tornado in Redding, California from the Carr Fire on the 26th July of 2018. So I think just from these two slides, we get a sense that we really can talk about various scales of meteorology that's related to fire. So the next slide, we're clearly undergoing a changing climate and its relation to wildland fire. And one of the ways to look at that is fuel aridity. This is driven by both temperature and atmospheric moisture. This is a paper from Abosco and Williams in the proceedings back in 2016. 8 different drought indicators that can be related to wildland fire, but looked at through the concept of fuel aridity. And basically all 8 are showing a trend of drying over the period 2000 to 2015. So this is, we should think about this as really there are three shaping factors for fire. Climate being one of them, fuels being another, and people being the third. So in the next slide, here's an example of the effects of fire exclusion. Bitterroot National Forest, 3 photographs taken from the same location, 1909, 1948, 1979. Notice that in 1909, the forests are wide open. Even horses are walking through the forest. In 1948, you start to see that fill in. And by 1979, it's completely filled in, all as a result of fire exclusion. There are many places across the West where this has taken place. And this, of course, is now an additive effect as to why we're seeing the fire behavior and the fire activity of these days. I'm not sure, but I think it's possible in that 1909 picture, the person standing there is a graduate student, and I think it's the same graduate student in 1948, and probably there in 1979, we just can't see them. On the next slide, this is the Tubbs fire. The red outline is the Tubbs fire perimeter in the Santa Rosa region from a few years back, 2018. And notice that the left panel shows 1940, and the darker colors show changes in housing units per square kilometer. And on the right is 2010. Now, there was a significant fire in 1964 called the Mahoney fire in this area. The perimeter was very nearly identical to the Tubbs fire perimeter. So the key thing that we're seeing here is how the population and housing are now building more and more into areas where fires do occur. They have occurred historically, they occur there naturally, and these are fire-prone areas. So now we have the three pieces, the three elements, the climate, the fuels, and the people, and all of these things work together. And even though when we do research, we'll focus on one, and we can focus very specifically about elements of one of these things, we really need to think more about how they all interact together because they are all so interconnected. The next slide, we can start to think about, well, where are areas for investment? There are two types of fire that we want to do this for. The first is wildfire, as seen on the image on the left, but also prescribed fire. And one of the ways, and very important way to manage wildland fire is through fuels management. And it's not just for the fire part, but it's also for landscape and ecosystem health that prescribed fire is important. So the 4 bullets below, suppression, fuels management, preparedness, prevention, these are primary programmatic areas within the wildland fire agencies. And in particular, suppression and fuels management are the areas probably most relevant for fire weather research to inform and to help with any strategic planning, tactical planning, decision processes. So the next slide depicts that really this is a continuum. If we think of this as both time and space, we can go back in time actually to set up a fire season. We could go back not only just the previous season or previous year, we can go back decades, or in the case of this fuel buildup, we can go back a century. But if we think about the research needs, I mean, often leading up to a season, we start with outlooks. These would be seasonal, monthly, and then they work their way into the shorter term, weekly or sub-seasonal, kinds of forecasts, week 1, week 2 kind of forecasts, and then work our way down into the next 48 hours, the next day, even down to today's forecast, and a very short-term forecast for a specific incident, whether that be a wildfire or a prescribed fire. And of course, this can occur very locally, but from a spatial perspective, there are products and needs that span actually globally, but for this conversation, we're probably talking more about national, regional, state, and the local levels. In the next slide, as Bill mentioned, there are many, many different areas that we can talk about for research ideas and investment in research. That spectrum really is long-term, climate to current weather. Some key areas that I see a lot that are taking place right now. A lot's going on in coupled fire weather modeling, smoke and air quality forecasting. This is an emerging and evolving area and important. It's related to human health impacts and firefighter health safety impacts. Drought and fire is ongoing, and of course climate change. There's a lot of research taking place there. The image that I have is just one example. There's an effort underway called the Fire and Smoke Model Evaluation Experiment. This is meant to be a grand experiment that includes the areas of scientific focus listed there on the right. It's an attempt to collect significant amount of data that can be used to improve modeling systems, prediction systems. But given everything that's going on, it seems like a lot of the research that's taking place is really more opportunistic, which is fine, and that can be very successful and certainly has its place. But I think one thing that's lacking, particularly in fire weather and fire meteorology kind of research, is really a lack of a national strategy or lack of national plan, that we don't really have a consistent mechanism to follow through to perform this research and actually use it, operationally, or to provide that decision support. And the last slide that I have here is there's barriers to adoption, of course. And in some ways, I thought this had been figured out back in the 1960s, but it seems like we're still fighting with it today. And one way to look at it is there are various stages of decision making, and there's the role of end users in the research process. And I think the most successful efforts are those that really integrate both the user community and the researcher community in a way that co-produces the outputs and co-produces the outcome. There's really these three general areas of research. There's basic, there's applied, there's the use inspired research. Basics, very fundamental knowledge. We get, and we need that, that's important. There are still things about fire physics that could be better understood. And then there's the application of that, and then there's actually getting it used in day to day. So I think with that, I'll end there, and Bill, and we can turn over to the next panelist.
All right, thank you very much, Tim. Our next speaker is Brian D'Agostino.
Yeah, thank you very much, Bill. Thank you to the panel. It's great to be here with you today, and for all the attendees. As Bill mentioned, my name is Brian D'Agostino. I am a meteorologist, and I'm the Director of Fire Science and Climate Adaptation for SDG&E. And as we head to the next slide, I'll quickly run through some of the things I'm going to cover and really, give the utility perspective and the meteorologist within the utilities perspective on what were our real challenges in 2020. The evolution of wildfire mitigation as an infrastructure provider in California, as we have seen this increase in wildfire, our risk management process and how we process and deal with this, and then where we are in terms of our analytics, right? And how are we integrating those analytics into our operations to make better decisions? And then where do we think this is going as we look forward? But I want to start off by looking back. The next slide, 2020, a very challenging year for us. And a lot of it starts with unprecedented heat across the Southwest. And as an infrastructure provider, I think we've all seen what the extreme cold did across portions of Texas and south central parts of the country this year. Well, the extreme heat last summer led to load curtailments and load shedding, rotating outages across the state of California. It also led to periods of extreme fire danger. So we did have the Valley Fire, almost 20,000 acres in San Diego. But in addition to that, we had public safety power shutoffs, which are now a major component of these extreme weather conditions, where we see an imminent risk to life and property due to high fire danger and the potential that the infrastructure could be an ignition source. So in advance of those extreme fire weather conditions, we de-energize the electric system for safety. Now it's a major step that we take in California, and it has major impacts on our community. So it is a big part of our risk mitigation in California, and one that is very dependent upon solid and accurate and precise weather information and weather forecasts to implement a program like that as responsibly as possible. Moving forward to the next slide. Last year, just quickly wanted to summarize the scope because it was truly unprecedented in terms of wildfire across the state of California. Over 4 million acres burned. That's more than twice the largest year before it, whereas back in 2018, we had almost 2 million acres. And 5 of the 6 largest fires in history were burning. What I found very unique, the August complex burned 1 million acres, and that's actually more acreage than all California fires on record combined between 1932 and 1999. So something is definitely changing. And then when I joined the team here, closely watching fires back in 2009, everyone said, oh, it's that fire season. It's late September through Thanksgiving in the fall. And during that, my 10 years at San Diego, I've seen 4 major fires take homes and really impact lives, and none have fallen in that window. They've all been in May of 2014, December. A lot of those are having to do with our extended droughts moving into shoulder seasons, lengthening the fire season across Southern California. And then we've seen extreme heat events where we have weak offshore flow driving temperatures up well over 110 degrees in our inland valleys, causing large fires in July of 2018 and then Labor Day of last year. So definitely seeing some changes to our climate history and some of our fires in San Diego and across California. Next slide talks about a perspective change, which we had across Southern California. And here in San Diego, we do have a large history of catastrophic fire. Started in 1970, we had the Laguna Fire. And as you heard from Tim, the footprint of that fire, if it were to happen again, there would be a lot more houses in that footprint this time around, and it hasn't burned since. So we watched that area extremely closely. But back in 2003, we were very focused on being compliant, right? Our regulators said, you have to operate to this way, and that was what we did. And we made sure we were compliant with the regulations. And then we realized around 2007, we need to go far above and beyond those regulations. And that's when science really became integrated in how we operate the system, how we harden the system, and how we really anticipate and prepare for extreme weather events so that we can mitigate and minimize the impact of wildfire ignitions, because that has become the core goal. At the end of the day, no wildfire ignitions is really what we're driving for. Next slide gets into a little bit more specifics. Situational awareness and weather technology drives a lot of what we've done. right, 10 years ago, started putting weather stations on every circuit we operate. We now, our service territory is about the size of Connecticut. We have 220 weather stations monitoring that region, and that feeds high resolution forecast modeling, which drives fire potential products that help us make decisions 365 days a year on how we operate the system. We also use that information to prioritize where do we harden the infrastructure first. There were some places where the civil code said we had to build the infrastructure to 56 miles per hour. We've measured winds over 100 in these areas during strong Santa Ana winds. So we're rewriting our design standards to really build the system to what can potentially happen during these extreme weather events. And then our meteorologists, our firefighters, our aviation folks, emergency managers, we're really bringing the subject matter experts into the management team within the utilities to make sure that our system operators and our engineers who are running this system are really teaming up with the science so that we can make the best decisions we can possible when trying to make sure we do not have ignitions moving forward. Next slide, please. And this looks at kind of how we've integrated the meteorology and the science into our core risk management at SDG&E. We do have an annual company-wide process to assess enterprise risk and inform how we spend our dollars to harden the infrastructure. And we do integrate that meteorology straight in. We look at specifically wildfire risk as a risk. We look at climate. And climate is a cross-cutting risk, right? So climate can impact wildfire, it can impact system integrity. So we now integrate climate into many of our enterprise risks across the utility. And then we take state-of-the-art modeling from weather forecasts and integrate it in to our risk-based modeling systems that determine exactly which poles and which areas of the electric system get hardened first. That's all being driven by weather models and the potential for extreme weather. And then we also take that into our consequence modeling. And we use weather to drive, if a fire starts in a particular area, what would be the risk to that community. So then we can actually harden those communities first because they're most at risk to wildfire starting from the electric infrastructure. I demonstrate that a little bit more on the next slide, where we end up looking at specifically our real-time fire behavior modeling, where we take information straight from our weather network, straight from our weather models, and feed it into fire behavior models. We'll simulate tens of millions of virtual wildfires every day and can tell us if a fire starts at this pole or this transformer, it could burn this many acres, could threaten this many homes, and then we can start operating the infrastructure with an additional level of conservatism to minimize that. Now we want to be careful because when you operate the infrastructure conservatively, that means more outages and longer outages. So it is a big balance that is very dependent upon good meteorology to strike that balance. The next slide is focusing on where our analytics are now and where we're really focusing on those next steps, and wind forecast modeling, the integration of AI, and using that 10 years of data collected from our Mesonet to train AI wind forecasting models that can inform those public safety power shutoff decisions that are so impactful to our communities and have to be approached very, very carefully and thoughtfully and scientifically. Our climate vulnerability assessments right now using climate models and the best climate science to make sure that as we are hardening that infrastructure now for wildfire, those hardening efforts will be resilient to our climate of the future, and making sure that we are building to the standards of mid-century and beyond and not the standards of the last 30 years. The fire behavior modeling I demonstrated, we continue to advance. And that's where Tim said fire science, and Bill said it as well. Fire science is very complex, and it is a rapidly maturing science, but one that we're trying to bring lots of real-time applications into that science. Real-time image analysis, not just from mountaintop cameras, but remote sensing from satellites. I think we saw that in Tim's example there. That is a really good way that we can advance and enhance our situational awareness through satellite and camera imagery and analysis, and then outage prediction moving forward. I think I've got one more slide, which wraps it up, and that's really just our journey moving forward. Innovation and continuous improvement. We are up, especially when we look at the utility, we're up against an increasing risk, increasing severity of weather events. What we did last year will not work next year. So we have to continue to try to stay ahead of this. And we do that through collaboration, working with the communities, working with first responders, working with fire agencies to continuously keep the communities that we serve as kind of that foundational value of what we're trying to improve the service that we provide. And we're going to continue to optimize all of our work moving forward and integrate as much meteorology and science as we can. So I'll leave that there as the introduction. I really look forward to the follow-up discussion. And then with that, Bill, I'll hand it back to you. Thank you.
All right, thank you, Brian. And yeah, the Western utilities are really in a tough spot, and it's pretty phenomenal what your meteorological group has done at San Diego Gas and Electric. It's phenomenal.
Thanks, Bill.
All right, next up from the National Weather Service, Robin Heffernan.
Thank you, Bill. Good afternoon, everyone. Like Bill said, I'm with the National Weather Service. I'm the National Fire Weather Science and Dissemination Meteorologist. And today we're going to have a little peek into some of the products and services that NOAA has for the fire community, where our recent advancements have been, and kind of what our challenges are going forward. Next slide, please. So here we're just going to look at a brief overview of a lot of our most critical fire weather products and services for you. Up here in the top left is our Storm Prediction Center. They issue a day 1, day 2, and day 3 through 8 fire weather outlook for areas of elevated or critical fire weather. And then as time gets a little bit closer and we have a little bit higher confidence in location of an event, severity of an event, the top middle right there, you'll see a red flag warning example showing our hazard products such as fire weather watches or red flag warnings will be issued by our 122 forecast offices when the elements meet criteria. In the top right, this is an image from our spot forecast page. This is an area where our close partners and emergency manager customers can come and request a site-specific spot forecast for a particular lawn piece of ground for whatever type of incident they're working on. Not just for fire, it could be for a search and rescue, it could be for hazmat, marine type of incident, whatever the case might be. But this is an opportunity for them to get a specifically tailored forecast for one particular spot on the landscape at very high resolution. And then finally, across the bottom of your screen here, we're highlighting our on-site incident meteorologists, or IMETs as we call them, and the wide array of forecast duties and services they provide. Everything from briefings, media interviews, setting up weather stations, releasing weather balloons and getting the radiosonde data back and analyzed, working in the field, and then the bottom right there, doing some storm assessments even when we have some fire tornado incidents that sadly are becoming more and more common as we go forward in time. Next page. So as we start developing our forecast information and what we want it to look like for the future, we start at the end state. We start at the decisions that our partners, our emergency managers, fire partners, land management agencies, the decisions they need to make. And then, next slide, please. And then we work backwards into the decision support information that they will need to inform those decisions. From there, next slide, please. We'll work backward one more step and determine what type of operations we need to provide, what type of forecast products and services and briefings are going to need to be provided as decision support. And then finally, back one more stage, next slide, please, to research. What science and technology gaps are there in order to provide this information? Where do we need to increase our skill? Where do we need to provide new products and services? And from there, next slide, please, that goes all the way forward again. So those new improvements in science and technology inform our operations, which therefore informs the decision support that we provide to our customers and partners, eventually making a positive impact on the final decision. So that's how we're working forward to improve our products and services. Next slide. Now I'd like to show you a few examples of some of our more recent improvements in these decision support products and services. First, we'll start off with the category of satellite data. And of course, this is our partners in NESDIS that are providing us this high resolution data that have improved our forecast capabilities within the National Weather Service considerably. In the top left, that's the GOES imagery. And that what we're trying to show here with this imagery is that this high temporal resolution of the new GOES series of satellites, east and west, has really allowed for fire detections to be noticed and notified to our fire partners quickly. It's allowing us from space to be able to see fire behavior and fire activity, which is very helpful even when on an incident. Sometimes there's too much smoke to be able to fly, some air recon and those types of things. And this satellite imagery is very valuable to our fire partners. On the bottom of the screen, there's our polar satellite series, JPSS. And if you can click play on there, it'll animate that a little bit for us. This is showing our fire, yes, there should be a play button right there on the bottom. If not, no worries. So the JPSS imagery is showing us very high spatial resolution data. So this is helping us be able to plot fire perimeters and those types of data, and also show fire growth. Once again, really helpful at all times, but also in areas where we don't have infrared aircraft. There's only 2 infrared aircraft that fly all of the fires in the West every single night. And as you can imagine, as our increasing fire activity over the past several years, there's no way they can get to all of them. And so this JPSS VIRS data has been incredibly valuable to supplement those flights. And then going back up to the top center here, this is our JPSS imagery showing us mapping of burn scar areas. And this is highlighting high risk areas for possible debris flow and flash flooding due to recent burn scars and in a period of any heavy rain. So once again, major improvements there in being able to warn our customers and the public of areas of possible flooding and debris flow threats. Next slide. Okay, now moving on into improved decision support in areas of high resolution modeling. So in the upper left there, that's our 1.33 kilometer NAM nest model with a mobile domain, and the imagery on the bottom there is from that as well. This model, in addition to our high resolution rapid refresh 3 kilometer model, are used to put as inputs into fire danger modeling, into fire behavior modeling, and for improved outputs from those modeling cases in order to be able to show us what the risk is for safety, but also for the tactical and strategic decisions that the fire managers need to make. And finally, that information also is input into our smoke modeling structure, which is what we're indicating in the top right picture right there. And next slide. And in addition to the high resolution meteorological models that are used as inputs into smoke modeling, we also use the JPSS VIRS data as well as inputs into our smoke modeling structure. In the top right, that's the HER smoke, high resolution rapid refresh smoke model. And this is used quite a bit in the fire community now, as you can see, for indications of both smoke concentration as well as smoke transport across the country. Now, this is very important, of course, for communities and public safety and air quality issues, but also as far as fire management goes, it's very useful information with regard to management of aviation resources on wildland fires and where those resources could be used. We don't want to have them smoked in an event and not be able to use those resources across the country. So for both strategic decisions as well as air quality and safety, these improvements have been considerable. Next slide. And then finally, a path forward here. Image on the right showing that NOAA support really is for the entire fire life cycle. It's not just for one particular piece of it, but the products and services we're developing, the decision support that we talked about in a meaningful forecast product, is being developed for every single element of the fire, including before the fire occurs and after the fire occurs with our post debris flow risk analysis. On the left here, I want to highlight a few areas, which is kind of areas for growth. these are not necessarily gaps. Some of them are gaps, but some of them are just areas that we need improvements in our data and our modeling and the resources that we have to make the advancements we need for our fire customers and for the public. So with regard to fire, smoke, and fuel observations, we need increased quality and increased density in these types of observations in order to enable early fire detection and real-time fire monitoring for spread and behavior forecasts as well. Meteorological observations, particularly in the boundary layer, that will allow for improved smoke and fire behavior analysis and forecasting. And then at our high latitudes as well. We're very data void in the high latitudes in Alaska, and we need some improved meteorological observations as well as forecast tools developed for those areas to improve our services there. Modeling improvements, improved modeling resolution, both spatial and temporal, will allow for fire spread and smoke predictions to be improved, also enables extreme fire behavior modeling and risk analyses as well. And then finally, decision support tools. As far as those go, we gave you quite a few examples here of some of our near-term and on-site type of meteorological tools and decision support tools, but where we really need the growth for the future is in actionable forecast information in the seasonal time frames, so that our customers can make those types of decisions far in advance of fire season starting, such as bringing on staff early and those types of things. So higher confidence and more tools in that environment. And that's all I have. Back to you, Bill.
Thank you, Robin. Boy, I tell you, last summer when we had the extreme fires going in every state and multiple fires, I really felt for the incident meteorologist. I really don't know how you could keep up with the extreme conditions that we've seen the last few years. So, kudos to the incident meteorologists.
Yeah, Bill, and it's actually been an entire office support effort these days. It's not just the incident meteorologists in the field, but we also have people that are staffing emergency operations centers at the state and those types of things. So those types of on-site support are expanding far beyond the fire itself.
Yeah, thank you. All right, thank you very much. Our next and final speaker is Nelson Breiner, who is with NIST. Nelson. And Nelson, you're muted.
Next slide, please. Thank you, Bill. NIST has been involved in urban fire research along with many other organizations for probably about 50 years. And there is hope if we can transfer the success from urban fires to the wildland or the wildland-urban interface fires. Over the last 50 years, a focused effort on different aspects of urban fires has cut the number of fires in half from over 2.5 million to about 1.3 million. The number of civilian fatalities have also been reduced by a factor of almost 3. And the total cost of urban fires is on the order of about $330 billion. For the wildland urban interface fires, significantly fewer fires at around 63,000. Of those that intrude into wildland urban interface area, probably something approaching 1,900. And unfortunately, that's an increasing number. The number of civilian fatalities are also increasing. Interestingly enough, it's about the same order of magnitude. It's about $175 billion in terms of total cost. Both of these different types of disasters. Next slide, please. If you look at the 15 largest fire incidents in the United States in terms of cost, again, the blue are the urban fires and the red are the wildland or wildland urban interface fires. And 7 of the 15 are actually wildland urban interface fires. And so that demonstrates, again, it's a very significant problem in terms of the overall costs. Next slide, please. Fire is, to a certain extent, fire. If you're going to mitigate it, whether it's urban or wildland, you need to prevent the ignition. Often this is done through ignition-resistant materials or designs. You can prevent the spread of the fire once it's ignited. So you limit the fire to a single area or single fuel package. You reduce that fire spread from fuel to fuel. And then suppression, whether you're in urban environments or wildland urban interface environments, water, foam, and chemicals. The ignition occurs typically through three mechanisms: flame contact, thermal radiation, or embers. Embers tend to play a bigger role in the wildland urban interface fires, causing up to 50% of the structure ignitions. Next slide, please. So the core capabilities that we maintain at NIST to address urban fire research, and we're beginning to transition into wildland urban interface fire, are fire resistant technologies, again, working that ignition resistant or limiting the fire spread, typically done through materials. We have a computational fire model, which for structures is considered to be state of the art. It's advanced to a stage where we can now reconstruct significant fires to try and understand what actually happened. The fire dynamic simulator is the name of this particular model. It was the one that was used to reconstruct the World Trade Center. It also was the one that was used to reconstruct the Rhode Island nightclub fire, where we lost 100 civilians. So this state-of-the-art model takes the different fuel properties, the geometries, the ignition points, and then propagates the fire through the structure in very small time steps, which helps to understand how the fire can move through the structure. It takes advantage of the fact that most structures have floors, walls, and ceilings. As we transition this fire model to the wildland urban interface fire, one of the difficulties is that not only do you have those structures, but you also have weather, such as wind, and you also have terrain. And how the wind and the terrain actually affect the fire spread is not as well understood as it needs to be. At NIST, we have a medium scale test facility, so we can test a 2-story structure under very careful conditions. That allows us to collect data. That in turn allows us to validate our model. We also work in advanced fire and smoke sensors, which have helped alert occupants to the fact that there's a fire much earlier in the development of the fire. And we also work with firefighting protective equipment and tactics. Next slide, please. So one can ask, has all this science-based research really improved the situation? In urban fires, it has dramatically. Science-based urban building and fire codes have hardened the structures to a very substantial degree. Typically, if a fire gets started in a room, it's often in that room when the fire department arrives. This is done through earlier detection. Fire-resistant materials, things like chairs, carpeting, and furnishings may have fire retardant qualities. The fire spread rate is typically very limited. You also have automatic water sprinklers, and compartmentalization can also help. There are some very specific impacts, 50% reduction in the number of fires and civilian fatalities. Again, we believe we've reduced the cost of commercial fire protection using the fire dynamic simulator by 20%. 30% reduction in terms of cigarette ignition deaths, a 20% decrease in mattress fire deaths. So these are measurable impacts that a prolonged effort in urban fire research has realized these impacts and have made a big difference. On the other hand, the wildland fires, wildland urban interface fires, there's much more limited science. We do a reasonable job of capturing flame contact and thermal radiation. We lack a lot of understanding as to how many embers it takes to ignite something, the size, the mass. I can't tell you how many embers arrive at any given time per square meter. Generation, there's been a lot of work done in transportation, but it's not there so that the models can predict when embers will actually ignite things. I mentioned earlier the impact of wind, terrain. There's a difference in vegetative fuels versus structural fuels, big impact of moisture content of the fuels. And so there's a lot of science that needs to be done on the wildland urban interface side of fires. We need to better understand. We need better science so that we can harden these structures. We've demonstrated that you can harden the structures in urban fires. You can make them much harder to ignite. If they do ignite, the fire doesn't spread as quickly. Not true in the wildland urban interface communities where they ignite very easily and then they burn very, very rapidly. I would estimate that the wildland urban interface fire science is probably about 40 years behind what we have in the urban fire codes at this time. Next slide, please. So more specifically, when we talk about data needs to advance wildland urban interface fire modeling, we need a better understanding of microfuel pyrolysis data, a wide variety of grass, shrubs, trees. We need the heat release rate, how fast the energy is released. We also need more data on fuel type. Yes, there are fuel mappings out there, but they're not done very frequently. If an area encounters a drought, you would need a more recent fuel mapping to understand what was there. Fuel moisture, again, understanding how to fuse that data from satellites, aerial and surface observations, again, in a very timely way. Doing it once every 3 months is certainly not fine enough resolution. Terrain data, again, we're getting we're getting better resolution from satellites, but drones can actually provide us probably something on the order of centimeter resolution. And if you're talking about fire modeling, you need to get down to somewhere in that range in order to be able to predict ignition and fire spread. The weather data, again, the possibility of using portable real-time measurements that actually arrive on the scene ahead of the fire and provide very current information would be invaluable. Next slide, please. In terms of the modeling, our current rate of spread models are rather basic. We need to have a better characterization of the physical processes, as well as how wind factors into that, terrain. Fuel mapping, again, being able to update the fuel maps in front of a fire in very short order would be very helpful. The ember transport and spot fires, we do not have currently don't have a very sophisticated ember transport model and ignition. So we can transport the embers. It's more difficult to predict how many embers it will take to ignite something. The smoke plume transport, again, taking the source term from the fire side of the house and moving it into the weather side of the house is going to be where a lot of the impact is had. The largest single component of those indirect costs for wildland urban interface fires is actually the smoke plume and the health effects downwind from the fire itself. And again, we need to be able to assimilate the on-site observations more quickly and incorporate them into the fire models, as opposed to currently we tend to start a fire model, let it run for a while, and don't change anything. We need to be able to change on the fly. And that, Bill, is all I have. Thank you.
Thank you, Nelson. That's a rich presentation of additional research and operational needs for sure. And the WUI, the Wildland Urban Interface, is absolutely critical in a critical area for us to improve our understanding. So thank you to all the speakers. We're now going to go into the Q&A part of the session. We have until 45 minutes after the hour. So we have a good amount of time for questions, and I'm going to try to do them in rough order that they came in. The first one is from David Lubar of Aerospace Corporation. He asked, what are the key contributions from satellite data for wildfire detection or management? What's the largest contribution from observations to wildland fire management or the timely warning of fire initiation? And I'll just mention one more thing. As a follow-up, he wanted to understand what, does the satellite contribution make any significant impact to the economics of wildfires? So let me open this up first to Robin and then Brian.
Hey, yeah, well, I can tell you the recent advancements in satellite detection of fires is a game changer, for sure. It has allowed our fire agencies to be notified significantly earlier than they would historically of these fires on the landscape. As the name alludes to, it's wildland fire. It's fire that occurs in areas that aren't highly populated, right? So it's hard for the public to do these 911 calls and report them, right? And there are observing towers that are around for these agencies to observe, but those are limited. Now we have up to minute updates of satellite data that's monitoring the entire landscape and being able to show fire detections as soon as they start. And with these fires and how fast they grow, minutes matter. So this has been incredibly significant change for the fire community as well as safety for the public.
Thank you, Robin. Brian?
Yeah, so when we look at, the overall fuels environment, that is one way that we're leveraging the remote sensing. So the NDVI is a really important component as we look at the greenness of the grass. And then, especially now with GOES 17, we're starting to look at how do we leverage that NDVI to try to improve our live fuel moisture modeling as well. So that's a big component. Also in the real-time alerting, right? As Robin mentioned, through work with University of Wisconsin, right? Getting the heat detection, because we could easily have 6 or 7 small ignitions even across San Diego County on a normal summer afternoon. So being able to get that alert and then use mountaintop cameras to get kind of real-time situational awareness, that's a combination that's been working really well.
And would either of you be able to weigh in on what would be the minimum resolution that would be useful for you in terms of the satellite data set? What grid cell would be the most accurate? Because certainly the satellite-based remote sensing resolution has been increasing and becoming more useful to truly target the heat and target the ignition locations. So do you have a sense for what the optimum grid spacing might be for these data sets?
Well, ideally less than 1 kilometer, and our polar satellites do that for us. Geostationary is a little bit higher than that, usually around 2 to 3 kilometer. But both of them are providing high value in being able to see fires, even with the geostationary satellites down to the structure level. We've had instances where folks have been able to see those fires.
Hey, Bill, I might add that another important use of satellite detection is for smoke and emissions. Having those real-time observations really helps be able to provide the inputs for those models to have more accurate predictions of PM 2.5 from smoke.
Absolutely. Good point. Okay, let me queue up the next question from Alec Krautman, Nesdis. It is for Brian. Impressive overview. What types of observations or data or forecasts are still most lacking or hardest to get for your utility?
From our standpoint, it is the fuel environment, right? And that is still the most difficult. So when the meteorological data, that's something that we have a pretty data-rich environment. But when it comes down to understanding the amount of moisture, and I think we saw this from Nelson as well, this is one of those areas where the science could be improved. And it's really understanding on many different levels the moisture content of the wildland vegetation and how that impacts combustion and fire growth is something we're still advancing as much as we can.
Thanks, Brian. Next question from Rick Rosen, AMS history. What are local communities doing to address their zoning regulations so that homes are being built in safer areas? Let's have Nelson take this one.
Thank you, Bill. So it's if we can understand how the terrain and the fuels interact, then it is possible to understand what areas one might not want to build in. NIST has developed a fire exposure scale, which does consider both ember exposure to embers, and thermal radiation type of exposures. And there are some areas that as a fire approaches a community, remember the periphery of the community is going to see both the thermal radiation from the fire and the embers, while the interior of the community is only typically going to see the ember assault. How you mitigate ember exposure is different than how you mitigate thermal exposure. So if the science were better developed, we would be able to say, okay, if you're going to build in this area, this is the type of hardening that you need to include. If you're on the interior of a development, then you might not need to build to the same standards. So there are trade-offs, between where you can build and the risk of exposure. Generally, once the science is developed, we provide that science to the standards and codes committees, and they incorporate it fairly quickly into the standards, which then results in communities that are more hardened. But right now, we need more science to support those code changes.
And Nelson, if you were a homeowner and wanting to invest in hardening your home, where would you go first? Would it be the roofing materials? Would that be the first thing you'd look at?
Well, if I had wood shingles, that'd be the first thing I'd eliminate. The asphalt shingles can be fairly fire resistant, but cementatious tiles, Spanish tiles, are basically non-combustible. They can provide much better ignition resistance than the other types of roofing materials. You have cementatious wallboard, hardy board that can be installed as siding as well. So yes, going to a less combustible type of material generally improves your ember resistance.
Okay, great, thank you. All right, next question from John Porter at AccuWeather. He says, this is an excellent discussion on an important topic. Is NOAA running any real-time WRF fire runs, the coupled atmosphere wildland fire model, in an R&D mode, and what are NOAA plans for the future? Robin.
So OAR, NOAA's OAR line office is where they've been running some of these WRF fire model runs. So largely, a lot of the model runs right now have been, to simulate fire behavior in order to project fire particulates and emissions for smoke forecasting. But we're looking in the future to expand that. They're looking in the future to expand that beyond that through actual fire behavior growth and spread.
Bill?
Yes.
This is Nelson. NIST has also been doing some limited runs that marry WRF with our fire dynamic simulator. The difficulty tends to be that the weather forecasting models deal in kilometers, and our structural or urban fire models work in centimeters to meters. And nesting those two grid resolutions together is a bit of an art right now. It's not a well-developed science, but we have had some success in marrying our fire model at the finer grid resolution to WRF at the coarser resolution. So the science is coming. It's not there yet.
Very good. Thank you, Nelson. And Tim, did you want to weigh in on that? No?
Yeah, I was just going to add that there is also a fair amount of work with this underway in academic communities. San Jose State University is one example. INCAR is another example of working with these fully coupled fire physics models. The question was about WRF, but there are other modeling efforts as well along these lines, and those can actually are being run at sub-kilometer scale, so it's not something you would do for the whole country, right, on a real time, but they can be done for individual fires. And in fact, there were lots of runs being done for last year's California fires.
And I'll just weigh in saying that, certainly the move towards exascale computing and utilizing GPUs can significantly impact the ability to run these models at finer resolutions over larger domains and more cheaply than a CPU-based system. So it's a very exciting area of research for the community, is to bring those type of capabilities forward to support predictive services.
And soon you can do it on your Apple Watch.
Very good. Okay, next question from John Zach from Mezzo Inc. For Brian. How do you measure the integrated effectiveness of your programs given that the external factors are changing significantly? For instance, aridity changes due to climate change, population distribution changes, et cetera.
Well, 3 thoughts come to mind with this. One, when we look at overall risk, we look at the potential for ignition, right, as one component, and then the consequence. And we showed that there is that fire behavior modeling with the consequence, but as we harden the electric system, we're changing that potential for an ignition. So we could look at 20 years worth of outage history and say, oh, this type of transformer has a 0.02% chance of starting a fire. Once we change it, it goes much lower than that. So that's one way that we can measure the effectiveness of the work. Another one is during public safety power shutoff, we do find damage to the electric system. So when the system is shut down and then we come back and we find a tree took down wires somewhere, we can then go in and use fire behavior modeling to actually then simulate fires from those locations. And that can tell us, had the system been energized, had a fire started, this could have been the potential outcome. So that's another way that we measure that. And lastly, what I wanted to mention is that through our enterprise risk management, we don't look at risks like wildfire and extreme heat as base flat risks that we're trying to mitigate. These risks are actually increasing over time. So we have to, in a sense, we have to mitigate faster than the risk is increasing, of course, to decrease our overall risk. But those were 3 thoughts, John, that came to mind. So just wanted to share those.
Thanks, Brian. All right, next question from Eric Grimmett, Weisla. He says mainly to Brian and Robin, but other panelists can also comment. In addition to satellite-based detection of wildfire ignitions and ladder forensics, what role do current ground-based observation networks play in your operations, such as lightning detection networks, radar networks, and other mesonet station data? There's a lot there, and they're all important, I can tell you. Why don't you go ahead, Robin, start with?
Well, certainly, like many areas in meteorology, it takes an all-encompassing approach, right, to see this. So we need to see our fire starts and our weather from the atmosphere, remote sensing. We also need to have our surface-based systems. We use our radiosonde data, and hopefully through time, increased network of LiDAR data for seeing the actual column of air and through the boundary layers. That's one area where we really have, I would say, a gap in data is when we're looking at the boundary layer observations. To have some continuous monitoring in that area just really isn't available to us at this point in time for our fire purposes. And it becomes very critical when it goes into smoke forecasting. So those are something we need. Of course, lightning, both from the satellites as well as the ground-based networks, are of critical importance to determine where new fire starts might be and those types of things. So yeah, it's an all-encompassing approach from all the different areas, radar as well.
Thank you, Robin. Brian?
Yeah, when we're anticipating an event, I would say the biggest value of all this ground-based observation data right now is the ability to train the AI model to see the next event coming, right? And that has been really how we've been leveraging, the billion weather observations that we've collected off our mesonet over the last decade, is that it is really helping to fine tune our forecasts. So that's a big one. Lightning, of course, low frequency, but high impact for us here in San Diego. So those are, we of course integrate in lightning detection, running the power grid. That's a big one for us that we leverage. But yeah, no, I would say overall, a lot of the value, and then of course, public safety power shutoff, right? We don't plan these outages. We wait for ground observations to tell us that our forecasts are verifying. And we will not turn off somebody's power until we start seeing an anomalous wind event materializing on the ground. So that's a kind of a critical component of the surface observations as well. Now I'll end it there.
Thanks, Brian.
Hey, Bill. Yes, all those networks, the things that Robin and Brian just highlighted are spot on. But I think an area, a gap that we have is consistent measurements, spatial measurements of fuels, and the characteristics of the fuels, the dryness and all those factors that are there in at least a quasi real-time mode to integrate into these different models. Satellite detection, as Brian mentioned earlier, with something like NDVI, you can begin to look at things like that. But I think a good network of fuel moisture, soil moisture, and the vegetation characteristics would be very helpful.
Yeah, Tim, I agree with you completely. We need much more frequently updated fuel map data and much more frequently updated and higher density observations of fuel moisture content for different fuel types. Absolutely, that's a key ingredient to wildland fire behavior prediction. A couple minutes left. I do have a question for Nelson. What is the insurance industry's role in addressing building standards?
Insurance companies can be a positive influence on not only supporting research necessary to address the problem, but also getting communities and individual homeowners to implement improved hardened structures. Sometimes, however, insurance companies will agree to build it as it was before. And so if you had wood shingles before, sometimes they end up with wood shingles again, which is not an optimal solution. But there are opportunities for insurance companies to not only characterize the risk a little bit better, and then help reduce the risk systematically. They are getting more involved. They are providing additional data on finer resolution than they used to. But again, there's still a ways to go in terms of mining that data that they have.
Thanks, Nelson. This has been a fantastic 75 minutes of presentation and discussion. The community is certainly going to need to pay attention to all of these topics and move out aggressively to try to catch up, as Nelson said, in wildland fire technologies and the adoption of new technology. So thank you to the panel. And without further ado, I'm going to hand it back over to Jen Sprague.
What a great panel. That 75 minutes went by very quickly and very informative. So thank you so much, Bill, for putting together a great session. And thank you to all of your panelists. We are going to break until 4 p.m. where we have Dr. Sean Miller leading, with Raytheon leading a great panel called An Update on the Latest Challenges and Opportunities in the Arctic. So we will see you back here in about 15 minutes and see you soon. Bye-bye.